Section 1.3 is about existence and uniqueness theorem. Sometimes you are given an initial first order differential equation such as dy dx is equal to f of xy subject to y of x0 is equal to y0. The goal is to find a particular solution to this differential equation which passes through this initial conditions. Geometrically, that's what initial value problems are all about, meaning find a solution to a differential equation which passes through that initial condition point. But the question arises that does this initial value problem have any solution? And if so, is the solution one of a kind, which means unique? So in other words, sometimes we are not interested in finding the solution, but we like to know if the solution exists, to an initial value problem. And if it does exist, is it one of a kind? In other words, do we have one and only one solution? So here is the theorem, uniqueness and existence theorem, which says, let fxy to be a continuous function on a closed rectangular region R, where a goes from a to b, y goes from c to d. If the function is continuous, that's condition one, and the partial derivative of the f with respect to y, not x, is also continuous in the same rectangular region, then for any interior point x0, y0 in R, there exists an interval, open interval I, containing x0, such that the IVP has a unique solution for all x in I. So what does that mean? That means if those conditions of uniqueness and existence theorem satisfies, then there must exist interior point x0, y0, such that our solution crosses that point only once, and all that happens in a rectangular region R, which is bounded by, x is bounded by a and b, and y is bounded by c and d. So they both are within a closed interval, and inside that rectangle, you can always find an open interval where the solution crosses the initial value problem once, and it just so happens it is the only curve which goes through that point and stays within the rectangle. So with that in mind, let's see if we can see or prove. Notice for the first time, we're trying to prove something, not compute something, which given this differential equation, 3xy to the power of 1/3, subject to y sub 0 is equal to 4, okay? Question is, can you prove that this solution has this differential equation has a unique solution? Remember, we are not supposed to solve for y. We're supposed to prove the solution exists and it's one of a kind based on the theorem which we just went over. So whatever is on the right side of dy dx is your fxy. So in this case, fxy is 3xy to the power of 1/3. Is this continuous function for all points on xy plane? Yes, it is. There is no discontinuity. In other words, this function, for no values of x and y, it's undefined or complex. So it's good to go. Now we take the partial derivative, that would be like condition 2, partial derivative of this function with respect to y. Remember, when you take the partial derivative with respect to y, you treat x's as if they were constant. So what happens is the partial derivative of f with respect to y, which is also shown as fy, for those of you who have taken multivariable calculus, 3x goes for the right because we take in the derivative with respect to y only. So all you have to do is take the derivative of y to the power of 1/3, which is 1/3 to the power of y to the power of -2/3. The 3's cancel. So you get x times y to the power of -2/3. However, This guy is also continuous, all points on x and y, except the ones who lies on the x-axis. In other words, y cannot be 0. Why is that? Because this guy is the same as x over y to the power of positive 2/3. And if y is 0, this fraction blows up. So what's the question? So what's the conclusion? So we can draw a rectangle containing what? 0, 1. So draw a rectangle which contains 0, 1, okay, that does not intersect the x-axis. That means all values of x and y is okay on the xy plane, except the values along the x-axis, because values along the x-axis, they have y equals 0, and when y is 0, this partial derivative becomes undefined, so it won't be continuous. Do you see it? So does not intersect, so take a rectangle which does not intersect the x-axis. So any such rectangle, the hypothesis of the existence and uniqueness are satisfied. Therefore, IVP does indeed have a unique solution. So the unique solution exists. Notice the initial condition is not even on the x-axis, so we are good. So take a rectangle, including the initial what? Enclose this initial point within a rectangle which does not go through the cross the x-axis. Like you cannot take a rectangle including what? 0, 1, which does cross the x-axis, because that would violate the condition number 2 of uniqueness and existence theorem. Do you see it? So we are good here, as long as you take the rectangle, what? Above, what? X-axis, including your initial condition, which is 0, 4. Okay, the uniqueness and existence theorem conditions are sufficient but not necessary. What does that mean? They are sufficient but not necessary. That means even though sometimes the condition may what? Fail, but that doesn't mean there is no unique solution. For instance, take a look at this example. d by dx is equal to 5 times y to the power of 4/5, subject to y sub 0 is equal to 0. Using the uniqueness and existence theorem, determine whether the given ODE with y sub 0 is equal to 0 has a unique solution or not. Once again, the idea is what? Do not solve. We are not supposed to solve this, even though it's easy to solve this equation for y. We're supposed to investigate and see if the conditions of the uniqueness and existence theorem are satisfied, so we can draw a valid conclusion. But we are not interested in solution. The idea here in this section is, does the solution exist? If it does, is it one of a kind? But what it is, we are not interested yet. Okay, so f of xy is the function on the right side, which in this case is 5y to the power of 4/5. Definitely is continuous for every order pair on x and y plane. However, the minute you take the what? Partial derivative of this, there is no x, so you just take the derivative of 5y to the power of 4/5. Excuse me. This guy is not continuous when what? When y is equal to 0. Can you see it? When y is equal to 0, this fraction blows up, becomes undefined. Therefore, the second condition, what? Is not satisfied for any rectangle containing 0, 0. Remember, the initial condition was 0, 0. And it just so happens this partial derivative is not continuous at 0. So therefore, the conclusion is the theorem does not guarantee a unique solution, which means we don't know whether there is a unique solution or not. Remember, just because the theorem does not guarantee it, that doesn't mean there is no unique solution. It just so happens the theorem doesn't guarantee it. It just so happens, I've already solved this with the initial condition, and it does have a unique solution, even though the theorem did not guarantee it. So that's why the conditions of the uniqueness and existence are sufficient, not necessary. In other words, there are times that one of the two conditions fail, but yet the solution exists, and it's what? One of a kind. So what about this guy? So once again, the problem begins by saying prove, not compute, but prove that this guy with initial condition of y sub 0 equals 3 has a unique solution. Remember, unique means one of a kind. One of a kind. There is only one solution which satisfies this differential equation and satisfies that unique initial condition. There's only one solution. Okay, so f of xy is the function on the right side. This guy is very much continuous for all order pairs in xy plane. Nothing makes this guy undefined. Notice this guy is always a positive answer. All right, take the partial derivative of this function, which is on the right side of dy dx with respect to y. So this is partial derivative. Remember, it's not this, okay? It's this notation, which means partial derivative. In other words, that's the kind of derivative we use for multivariable functions. Remember, the function here is in terms of what? X and y. So those are the independent variable. The dependent variable is f. So how do you do this? This guy is constant because the partial derivative is taken with respect to y, so that guy goes for the right. All you have to do is take the derivative of y squared minus 1 with respect to y, which is 2y, and you get this. This guy is also continuous for all order pairs in xy plane because no order pair makes this guy undefined. Therefore, both conditions of what? Uniqueness and existence theorem have been satisfied. So the initial value problem stated above has a unique solution on any interval containing what? Y sub 0 is equal to 3. As a matter of fact, any function, regardless of what x is, as long as it's equal to 3, is a unique solution. The type of function solutions where the answer comes up to what? Constant, those are called singular solutions. And therefore, there is no general solution. So that means there are no arbitrary constants. So do you see it? So y equals 3, period. Sometimes you can even tell what the solution is without solving the equation. Check this one out. Cosine square of x, y prime, equals y squared times y minus 1 times sine of x. By inspection, you can tell if you set these two guys equal to 0, right? Either what? Y is equal to 0 or y is equal to 1. And guess what? Those are the solutions to this differential equation, and they happen to be called singular solutions. Thank you.